Hello, everybody. I'm very glad to have this opportunity to give a presentation about our recent work on new fluid kinematics and fluid dynamics. That's the outlines of my talk. First, I want to give a brief introduction for nutex, which is a mathematical definition for vortex. Actually, nutex, it is a vector. The direction is the real eigenvector of the velocity gradient tensor and magnitude given by this formula. Here, omega is a vorticity, or is the real eigenvector of velocity gradient tensor. Lambda Ci is the imaginary part of the complex eigenvalue. This formula is given by Wang and others in 2019. Wang is the chairman of this workshop. First, we take a look about the traditional Helmholtz or Cauchy-Stokes tensor decomposition. The velocity gradient tensor can be decomposed to be A and B. A we call the strain part, which is symmetric. B we call the vorticity part, which is anti-symmetric. People usually think A is deformation, B is for rotation, but unfortunately, that's not true. So there are several problems because first, the vorticity cannot represent fluid rotation. The vorticity center tensor is really a mixture of rigid rotation and non-rotating shear. The symmetric strain rate tensor is a mixture really of the stretch and symmetric shear. Or we say diagonal part and off-diagonal part. But they are dependent on the coordinates. Therefore, the Cauchy-Stokes decomposition really is dependent on the coordinate system. Therefore, we want to set up a unique, we call principal coordinate system. And we can find the principal matrix. Note that tensor is unique, matrix is not. We need to give a principal coordinate. Then we can get the principal matrix. This principal coordinate is as a z direction is parallel to nutex, and the other plane is orthogonal to the nutex. So in these coordinates, we can get the we call principal matrix like this. Here, or we know it is a nutex. Epsilon, Xi, eta are three shear part. Lambda Ci, lambda R are stretching part. They are real eigenvalue and real part of complex eigenvalues. If in the principal coordinates we get the principal matrix, it's easily to be decomposed to be three parts. Actually, there's three matrices. First one is rotation. The second one is stretching and compression. The third one is shear. We call it R, SC, and S. So velocity gradient tensor can be decomposed to rotation, stretching, and shear parts. But this decomposition at each point, really is each vortex point, we must go back to the originally Cartesian coordinates. Otherwise, we cannot do any kind of operation like differentiation or integration. So because we use the P rotation and Q rotation, we need to rotate back to the originally XY coordinate system. So then we get three parts. We call R tilt rotation, S tilt shear, and C tilt is shear and compression. Well, all the rotating part is easy to get. SC we can get as well, which have two parts. It depends on if you don't have Newton, don't have vortex, don't have rotation, so this part will be zero. S is more complicated. You can see our recent paper called Newton's new fluid kinematics, published in GHD. Here we need to emphasize the vorticity should be decomposed to be R and S. R is rotation. S is non-rotating shear. That's easily be get. Also, this decomposition, it is not related to the coordinates. It's gardening invariant. Any coordinates. Vorticity should be decomposed to the Newton's and shear, what we call the vorticity or S decomposition. Look at this computational results. This is DNS for the flow transition. We pick a point from the leg of our lambda vortex. Because we can easily define it. The R is Newton's rotation. Vorticity is omega. Vorticity and Newton's, they are totally different. The vorticity pretty much contain the shear, not the Newton's. Newton's is only a small part of the vorticity. Anyway, vorticity cannot be used to represent the rotation. Same thing for other points, like hairpin vortex point. We also can find that the vorticity is very different from rotation. They're pretty much close to shear, non-rotating shear. Anyway, vorticity cannot be used to represent the flow rotation of vortex, especially near the boundary. We also derive what we call the UTA or in or tensor decomposition. Yeah, that means velocity gradient tensor is decomposed to the rotated and non-rotated part. Where the rotated part is Newton's, of course. And it is also easy to do in the originally X, Y, Z coordinate system. This is rotating part, this is non-rotation part. But now we talk about the new fluid dynamics. First, we need to give some mathematical foundation. the theorem 1 and just say the divergence of velocity gradient tensor transpose equal to gradient of divergence of what is velocity. This is easy to prove. According to this, we can get the corollary 1. The velocity, gradient, strain, symmetric, vorticity, antisymmetric, they are transferred. They transfer to each other by this formula. This is symmetric strain. This is vorticity. This is velocity gradient tensor. You see, they have relation. Of course, there's a term of divergence or velocity, but they transfer. For incompressible flow, that's very easy because the divergence of velocity is 0. Then you will see that's the strain, that's the vorticity, that's the velocity gradient and tensor. They are equivalent. So that you can use any one of them. So now is 3 questions. They just assume strain is symmetric and stress is proportional to strain. The Stokes assumption. Both strain and stress are symmetric. There's no rules vorticity. Our new governing equations assume stress is proportional to vorticity. Both vorticity and stress are anti-symmetric. There's no rules for symmetric strain, but actually both strain and vorticity have rules, as we show. They are equivalent. So that's originally, and now it's 3 questions. You look, that's the new governing equations. Look at their difference. Their difference, the first, the original, now it's Stokes questions. Use strain, which is symmetric. But the new governing equation use the vorticity. Of course, they have some change in the divergence of velocity terms. So the negative 2/3 become 4 positive 4/3. That's the new governing equations. They use vorticity only. Therefore, we just use vorticity because this is antisymmetric. We only have 3 terms, the omega x, omega y, and omega z. Similar to the stress. That's the original, now is 3 questions, stress. And that's the new governing equation. So the difference it is in the new governing equations, but this term only has 3 terms. I is not equal j. We don't need to use that term. But original now is 3 equations has 6 independent elements because they are symmetric. For incompressible, it's even simpler. So the now is original now is 3 questions. It's not that. They use strain. But the new governing equation, they use vorticity. Well, it looks similar. But the velocity gradient tensor has 9 terms. Strain, symmetric strain, has 6 terms. But the vorticity only have 3 terms. The computation cost is cut half. Okay, we already showed they're all equivalent. Then we check by computation results. First example is 2D backstep laminar flow. So the computation for original now is 3 question is red triangle. The pupil one, it is circle. So we can easily find it as almost the same for laminar flow. For the turbulent flow in S-Dark, of course, we have to use the model. If we use the same model like this, the original one use some model is the pupil. The new governing equations is green. They're almost the same if we use the same model. So the computation results prove they are almost equivalent. The conclusion is we know the velocity gradient tensor is unique, but we must define the matrix. It also should be unique, but in general it's not. So we give a principal decomposition, which is unique in the principal coordinates. The principal decomposition also can be done in the original Cartesian coordinates. The stress calculated by the velocity gradient or by the symmetric strain or by the vorticity, they are equivalent. However, velocity gradient tensor has 9 elements. Symmetric strain has 6, but vorticity only has 3 because it's anti-symmetric. The new governing equations by vorticity is Gaussian invariant, simpler, and has clearly physical meaning because the off-diagonal elements are just anti-symmetric share. So the new governing equations has vorticity, but now its structure does not have. The vorticity can be further decomposed to rigid rotation and pure anti-symmetric shear. This may be useful for turbulent research. There is no reason, after our discussion about why we don't use the new governing equations to replace Navier-Stokes equations, especially for incompressible flow. You save half in the viscous term. That's my conclusion. That's the reason of publications. and the most recent one is new governing equations of fluid dynamics. Is published in the ARP Advances. We already published 3 professional books and over 40 SCI papers for new text and others. Well, that's the movie for the fluid transition. I don't think I have enough time to show that. Thank you.